So we're going to take basically everything we learned in the class so far, from shear moment diagrams, from the critical location to beam stresses, stator stress, and put it all together in a one realistic problem. And the problem is about a machine, a design shaft. We want to design the shaft, and to design it, we want to identify the critical location of it. So let's go ahead and see this example. Um, so in this particular example, and you can pause. This is again part of my notes. You can pause. You can look for my notes, the online version of the notes, and this is the example 5.5 on page 356. From this particular example, this design shaft somehow reduces to this. These are the real actual loads acting on it after we replace everything. And these are the reaction loads are given in blue, and the other ones are actually applied load. And what you ask in this problem is to identify which is the design point. So to do the design point, the first part we have to do in this problem is to identify what is the critical location in X. To identify my critical location in X, I need to do 3 section cuts, right? Because I got 1 discontinuity, 2 discontinuities. So there's a section cut, and a section cut. I need to draw my shear moment diagrams, which I did this for you. And the shear moment diagram looks like this. Now, the goal of this exercise is not to show you how to find the shear moment diagram, but rather than keep moving forward. However, in this particular example, when we are doing this, this is what the shear moment diagram, all the load diagrams look like. Sorry, you got NXX, VY, MZZ, and MXX. So one of the things that we can immediately realize is the location where I want the moment to be maximum. This is the location of moment maximum, and so is the torque. But it happens on this side, happens on 5 plus. Now on 5 minus, yeah, this value remains the same, but my torque value is 0, whereas here the torque value is 1,000. So this is a location of maximum torque. And I really don't need these that much, but however, if you look at it, I still have some value there, and my axial load is also maximum. You could make the argument and say, hey, 10 plus also seems to be a possibility, because I have maximum, as you can see, you can say I have maximum shear here in the positive sense. So this could be critical, and this may not be that maximum, but maybe compensated by that. In the example in my notes, online version of the notes, I actually checked it and was able to show that indeed that's not the critical location. So for this example, I'm going to just limit myself and say this is the critical location in X. So X critical is 5 plus. And to better understand what the loads look like, we can go and draw a straight line here and just roughly on this side and find the values. The values are positive 50 pounds, positive 1,250 inches pound, 1,000 inches pound for torque, and 50 pounds for my axial load. So these are the loads acting on this cross section. So the next thing I need to do is I need to find my sectional properties to find my dimensions. So to do that, we can see that the problem that we have is a solid circle. And the problem does say that the circle has 1 inch, is 1 inch diameter. So you can see that your Z value from here your z is equal to pi dq over 32. This is a very good number to memorize, especially for shaft analysis. It's always the same number, and it becomes very handy and very useful. So if we plug in the numbers here, 1 inch cube divided by 32, you will see that you get a value of 0.0982 inches cubed. This is the value of z. Remember, z is used when I calculate the bending. That would be m over z. Okay, that's where I use the value of z. The second thing, I need to know what this is going to, my area effective is, because I want to find my tau that's V over A effective. And this is circular. So for a circular case, area, first of all, area of the cross section is equal to pi d squared over 4. That gives me 4.854 inches squared. So the area effective is nothing else than 3/4 of my A. So that would give me 0.5890 inches squared. So that's my effective area that's going to go in my tile. And for my axial load, for my axial load, this is the area I will use. This is the area that's used for P over A for my axial load, and this is the area used for my tau. For my torsion, we can come to this table, and you can see that for the case for torsion, I need to find my Q. To find your Q, you might say, I don't have a circle. Well, you have an ellipse, that's AABB, right? And so you could say this is pi, where A is equal to B is equal to 2, but note that this is half. So actually, you have to take this and you say this is the same as d over 2. So you replace d over 2, you can show that this gives you d cubed over 16. This is another number that's very handy to memorize in the design of shafts. And that gives me a value of 0.1635. So I got these values. Now we can move on to do our calculations. So before we start anything, let's calculate all the stresses. The stresses for my bending, we know that it's going to act in the x-axis and it's going to be B. It's going to be m over z, okay, where your m is equal to 1250 and your z is equal to 0.0982. And if you evaluate this, this gives you 12.732 KSI. If I calculate what my axial load is, this would be NXX divided by A. This was 50. Again, comes from here. They have the value of 50. And my area is 0.7854. 0.7854. And I get a value of 64 63.662 KSI. This is PSI. So to have everything in KSI, this is 0.0637 KSI. And again, compare these values, you can see how small the contribution is. The next quantity that I need is my V. We will worry about the subscript later, and that will give you the value Vy of area effective. And that value is, this was 50. And the area effective is 0.589, 0.589, and you get a value of 0.0849 KSI. Again, see the contribution of the shear is very, very small. And then we can also calculate the torque, T over Q. Torque was 1,000. Again, comes from this value, is 1,000. And it's the value of Q is 1964. And that gives you a value of 5.0930 KSI. Again, compare these values, you see that the contribution of this guy is very small to this. So we got all the values, we know what the values are now, and we can see that these are, in our problem, they were all positive, okay? So these are the values I have now. So if I go and build our table again, so the value that we have, let's build that table. So we're going to start building the table where this is your point A. Point A, your point B, point C, point D, point E. And we're going to start with your axial load. For the axial load, again, it's all positive. Since it's all positive values, then what's going to happen is the value of the axial load is all positive. So that means that all the points in my cross section, A, B, C, D, and E, are going to have the same value, and they will have the same value, P over A, and it will be all positive. So with that said, the value that we got was 0.0637, 0.0637, 0.0637, 0.0637, 0.0637, 0.0637. Now we can do bending and realize that the value of bending in this problem, the bending stress is positive, okay? So it's positive. So if I take this value and we see what happens for the case of this is completely positive, okay? So this is the value that we are getting for bending. So if it's positive, we know immediately that the way your stress is working, is acting here, is this is like this and this is like this. Okay, remember where this is your moment was positive. You have to look at your moment value. Your moment was positive. So this is your sign convention. So what this is telling you right now, this gives you a positive value, but you have to look at your moment. So it's actually giving you just the magnitude of that. So that means that when I do my diagram now, this value has to be negative, minus 12,732. this value has to be positive 12.32, and all others are completely zero because this is the neutral axis. So only A and B will have non-zero values. So it's 12.732 negative. This is zero. These are all zero values, and this is positive 12.732. The next item that we're going to look at is shear, the shear load. So for the shear load, note that the value of shear was positive in this sense. So if I do my cross section is A, B, C, D, I have E, and then your load is acting always in the same direction of this load. The stress will be in the same direction. So it's acting in the X plane in the Y direction, and it's due to B. And the value of my stress will be is 0.0849. 0.0849 had to be zero at the upper and the lower fibers. So if I replace that in my equations now, oops, is zero here. This is 0.0849, 0.0849, 0.0849, and then the next thing that we want to do in the problem is we want to do the torque. That's the next item to look at, is the torque. So when I do the torque, we can see that my torque was positive. My torque value was positive. So I have to draw this circle looking at front, A, B, C, D, E, and you can see that it's positive. So you can immediately see what's happening here. Here, this is going in this direction. This is coming in this direction because it's a torque. Think about like a couple that's actually making this spin, and this is completely zero there. So here, the value of my torque was, we just calculated this, 0.39 is 5.039. .93, sorry. So here you have to now put the axis. So this is acting in the x-axis because this is the x-axis, but it's acting in the z direction. Remember, this is z and this is y. This is our sign convention. So acting in the z and it's acting positive. Okay, so we can go here and say point A is positive 5.093. And let's do it, tau x z. Okay, so if I go to this point, it's acting in the x plane, but it's acting now in the y direction, and it has a minus sign. You can see it, right? Because this y is positive upwards, this is negative. So now we go here, and we have to say tau x y. This is minus 0.0 93. Go to point C now. Point C is acting in the x plane in the z direction, but negative, because z is positive. This direction is going in the opposite direction. So this will be tau xz will be minus 5093. And obviously this is 0. Let's put the 0 there. And d then would be, is acting in the x plane, but in the y direction, and is positive. Okay, so then we fill the table. This is tau xy, and this is positive 5.093. This is what your state of stress looks like. This is xy, this is xy, this is xy, and these obviously are sigma xx, and remember, they get added up. Okay, so now you want to build your state of stress. All you have to do is take these numbers, you add them up, and you build the state of stress. Like for instance, for this particular case, your state of stress of A would be 0.0637 minus 12.332. That's bending. XX. I don't have nothing here. This is 5.093. Everything else is 0. 5.093. And you can see that almost every point I get the point acts like a plane stress problem, right? You can see it's all zeros. Typically, that's the behavior you're going to get. Let's look at this point. At this point, then here it's kind of the same as this one. You're just adding these values. So 0 is minus 5.09 minus 5.09, 0, 0, 0, 0. Okay, so what happens here now is you need to say which one is more critical, and you can see immediately this is minus, right? This is plus. So what's happening here is here you're subtracting, here you are adding. The minus doesn't matter here because they are separate identity. You're not adding or subtracting. So at the end of the day, these are independent from each other. So this becomes the critical point. This will be the critical point in the problem. Remember, it's always driven by torque and bending. Okay, that's what's the most important thing in the problem. Now you could also run the MATLAB code. I have a MATLAB code that's called the design point. The point, what it does is, all you have to do is you need to manually enter these values. What is the length? What is your Q? What is your A? You need to enter these values. This value you have to manually enter. Then just write your shear moment diagrams, what they look like. You probably have that copy paste from your previous homework. So these are the shear moment, these are the load diagrams for this problem. And then rest of it, you just run the code. Okay, so if you run it, it's going to ask you, as usual, the system of units. Let's say KSI, that's what we are working with. And it's kind of neat what the code does. I don't want to go over that. Just give me a sec. So this is the load diagram that I gave you at the beginning. That's what I use. It gives you the load diagram, but it gives you something very interesting and very handy for you to use. Getting lost here. It gives you something, a file called the critical stresses. The critical stresses basically are the maximal stress, the minimum principal stress, the von Mises stress, and the maximum shear stress. This is your, I think I got this, swipe that while we fix it. Um, so what you're really doing here is you can see that if you're going to choose the critical location, and this is point A, point B, point C, and point D, you're finding the principal stresses for each one of those cases. You can see that this is going to be the critical location, which we already decided. But then point A, you can see that your point A, this is your point C, stresses are higher. Then the stress distribution across your entire domain for your point B, D, and C are over here. So you know that this is still the most critical one. Okay, so according to my maximum stress is point C is critical. According to my S3, now it kind of swaps because I'm using the negative value, but this is the mirror of this plot. So what we are saying is this is good enough. So point A is still critical. And if I want to look at my von Mises stress, what happens to a von Mises stress? What is showing you the von Mises stress is also critical in point A and C, they are identical. And all the other stresses are smaller than that. If I'm going to look at my maximum shear stress, the maximum shear stress tells me, what it shows me is that point A and C also have the same shear distribution. So indeed, point C, our assumption of choosing point C is correct, and that's what the plot tells you. So what I'm expecting for you to do for your homework from now on, I'm expecting you to do is try to understand what is going on, do it manually, and then run the plot and compare your answers. And that's what you should merge. Okay, this concludes your discussion for example number 1.